What if I told you that the ancient world was far more advanced than we've ever imagined? Picture this: 2,000 years ago, someone built a device so precise it could predict cosmic events with astonishing accuracy. No, this isn't science fiction. It's the Antikythera Mechanism, a bronze marvel from ancient Greece that functioned like the world's first analog computer. And that's just the beginning. Across the globe, civilizations long before ours cracked codes of nature, engineered miracles, and unlocked secrets of the universe without the tools we take for granted today. Think about that for a moment. We often assume progress moves in a straight line, that our modern era stands at the pinnacle of human achievement, but history tells a different story. The deeper we dig, the more we uncover traces of genius that defy time. Ancient doctors performed brain surgery. Mathematicians calculated the circumference of the Earth with shocking precision. Engineers designed buildings that still baffle us with their resilience. These weren't lucky guesses or happy accidents. They were the result of careful observation, relentless curiosity, and knowledge passed down through generations, knowledge that sometimes vanished, only to be rediscovered centuries later. This is more than just a list of forgotten inventions. It's a testament to human ingenuity, a reminder that brilliance isn't confined to any one era. So today, we're journeying through 30 of history's most astonishing scientific discoveries, each one a window into minds that saw farther than their time should have allowed. Some of these breakthroughs will make you question everything you thought you knew about the past. Others might even leave you wondering, if they could achieve so much with so little, what does that say about us? Get ready, because the ancient world is about to surprise you in ways you never saw coming. Buried beneath the waves for over 2,000 years, the Antikythera Mechanism was discovered by sponge divers in 1901, lying among the ruins of a Roman-era shipwreck near the Greek island of Antikythera. At first glance, it looked like nothing more than a lump of corroded bronze. But when archaeologists painstakingly cleaned and examined it, they uncovered something extraordinary. A complex clockwork device with at least 30 interlocking gears precisely cut from hand-worked metal. This wasn't just an ancient trinket, it was a machine capable of tracking the movements of the sun, moon, and planets with staggering accuracy, predicting eclipses years in advance and even accounting for irregularities in the moon's orbit. What makes this discovery so astonishing is the sheer sophistication of its design. The device functioned like a cosmic calendar, with dials displaying celestial cycles that would take modern astronomers advanced mathematics to replicate. One gear alone modeled the Metonic cycle, a 19-year pattern of lunar phases, while another recreated the Saros cycle, predicting when eclipses would darken the skies. The level of miniaturization and precision in its gears rivals that of 18th-century Swiss clocks, yet it was crafted over 2 millennia ago. But here's the real mystery: we still don't know who built it. Some scholars point to the genius of Archimedes, the legendary inventor said to have crafted celestial models so advanced, Roman soldiers supposedly mistook them for magic when they looted his workshop. Others believe it hailed from the workshops of Rhodes, an island renowned for its mechanical innovations. What we do know is that nothing like it appears again in the historical record for more than 1,000 years. Its existence forces us to rewrite the story of ancient technology, proving that the seeds of mechanical computing were planted far earlier than we ever imagined. Perhaps the most haunting question isn't how it was made, but how much knowledge was lost. The Antikythera Mechanism wasn't just a lone marvel. It hints at a forgotten world of scientific instruments, a tradition of craftsmanship and astronomy that vanished beneath the tides of time. If this single device survived by chance, what other wonders were swallowed by history? Fire that couldn't be extinguished by water sounds like something out of a myth, but for enemies of the Byzantine Empire, it was a terrifying reality. Known as Greek fire, this mysterious weapon gave Constantinople an unstoppable edge in naval battles for centuries. Picture the scene, enemy ships closing in, only to be met with a torrent of liquid flames that clung to wood and flesh, burning even as waves crashed over them. Sailors who leaped into the sea to escape found the fire following them, turning the water itself into a deadly trap. The exact recipe for Greek fire remains one of history's best-kept secrets, lost when the Byzantine Empire fell. Ancient accounts describe it as a sticky, gel-like substance launched from tubes or siphons, igniting on contact and resisting all attempts to douse it. Some historians speculate it contained a mix of quicklime, naphtha, and sulfur ingredients that, when combined, could create a chemical reaction fierce enough to burn on water. Others point to crude oil from natural seepages near the Black Sea, distilled into something far more volatile. But what made it truly unbeatable was its delivery system. Pressurized bronze pumps allowed Byzantine ships to spray it in continuous streams like ancient flamethrowers, with a range that outmatched any weapon of its time. Its impact on warfare was profound. In the 7th century, as Arab fleets besieged Constantinople, Greek fire turned the tide, saving the empire from collapse. The psychological effect was just as potent. Opponents fled at the mere rumor of its use, and its secrecy only amplified the fear. Emperors guarded the formula as tightly as state secrets, passing it orally from one generation to the next. Craftsmen who mixed it reportedly worked in isolated workshops, their knowledge so compartmentalized that no single person knew the entire process. Yet for all its power, Greek fire's greatest legacy might be the questions it leaves unanswered. Why did such a revolutionary technology vanish? Some argue the fall of Constantinople scattered its keepers before they could pass on the knowledge. Others believe the ingredients became too scarce, or that later chemists simply couldn't replicate the formula's precision. Whatever the case, its disappearance reminds us how fragile advanced knowledge can be, how easily a breakthrough that shaped history might slip through our fingers, leaving behind only echoes of its brilliance. And that's the irony. A weapon designed to intimidate and destroy became, in its absence, a symbol of how much we still have to learn from the past. The flames that once lit up battles now illuminate the gaps in our understanding, challenging us to ask what other secrets the ancients took with them. While modern concrete crumbles after mere decades, some Roman structures have stood strong for over 2,000 years, defying earthquakes, wars, and even the relentless wear of seawater. The secret, a recipe so advanced that scientists are still racing to decode its mysteries. Unlike today's concrete, which weakens over time, Roman mixtures actually grow stronger with age. The key lies in a volcanic ingredient they called pulvis puteolinus, a fine ash mine from the outskirts of Pompeii. When mixed with lime and seawater, it triggered a chemical reaction that formed ultra-durable crystals within the material. But the real marvel is how it heals itself. Microscopic cracks that would spell doom for modern structures, the Romans built them to repair automatically. Recent studies reveal the astonishing mechanism behind this ancient innovation. As water seeps into cracks, it dissolves traces of unreactive lime still present in the concrete. This forms a calcium-rich solution that recrystallizes, fusing the gaps shut, a process that repeats endlessly. Modern engineers have tried to replicate it, but there's a catch. The volcanic ash the Romans used came from specific deposits with rare minerals, and their exact mixing techniques were lost when the empire fell. Compare that to today's concrete, which relies heavily on Portland cement, a 19th century invention prone to erosion, especially in marine environments. The difference is staggering. Walk through the ruins of the Portus Cossonus harbor, submerged in the Mediterranean for 2 millennia, and you'll find its concrete piers intact, while modern docks nearby require constant repairs. What's most humbling isn't just the material's resilience, but the philosophy behind it. Roman engineers didn't just build for their lifetimes, they built for eternity. Structures like the Pantheon with its unreinforced concrete dome, or the breakwaters at Caesarea, still functional after 2,000 years of ocean waves, stand as silent rebukes to our throwaway infrastructure. Today, we prioritize speed and cost over longevity, pouring concrete designed to last 50 years at best. Meanwhile, the Colosseum, a structure that survived earthquakes, fires, and stone looters, remains a monument not just to empire but to the lost science of endurance. Perhaps the lesson isn't just about chemistry but vision. The Romans treated construction as a dialogue with time, crafting materials that adapted to their environment instead of fighting it. As coastal cities today grapple with rising seas and crumbling seawalls, we're left to wonder what other ancient wisdom might hold the key to building a future that lasts. In a basement of Iraq's National Museum sits a cluster of unassuming clay jars, each about the size of a fist, sealed with asphalt and fitted with an iron rod encased in a copper cylinder. Discovered in 1936 near Baghdad, these 2,000-year-old artifacts might just rewrite the history of electricity. Dubbed the Baghdad Battery, these curious vessels have sparked decades of debate. Were they ancient power sources or something else entirely? At first glance, the design seems eerily familiar to a modern battery. Fill the jar with an acidic liquid like vinegar or grape juice, and the interaction between the iron and copper creates a small electric charge, enough to produce roughly 1 volt of electricity. Replicas have proven it works, leading some researchers to speculate these could have been used for electroplating gold onto silver objects, a technique known in Mesopotamia for crafting intricate jewelry. Imagine a Parthian artisan using these primitive cells to gild a ceremonial cup, centuries before Alessandro Volta invented the first official battery in 1800. But not everyone's convinced. Skeptics argue that if these were truly batteries, why have we never found wires or connected vessels to increase their power? Alternative theories suggest they might have held sacred scrolls, their metal components merely decayed parchment rollers. Others propose they stored medicinal herbs, with the acidic liquid acting as a preservative. The asphalt seal, while excellent for preventing leaks in an electrochemical cell, could just as easily have kept precious oils or perfumes from evaporating. Here's where the mystery deepens. No contemporary texts mention these jars, leaving us to piece together their purpose from fragments. Yet the electroplating theory gains traction when you consider the advanced metalwork of the era. The Parthians were master goldsmiths, and surviving artifacts show gilding too precise for traditional methods. Could they have stumbled upon electrochemistry by accident, harnessing it without fully understanding the science? What's undeniable is the ingenuity behind these objects. Even if they weren't batteries, their construction reveals a sophistication we rarely attribute to ancient technologists. The combination of materials iron, copper, and an electrolyte shows an intuitive grasp of conductive properties, whether intentional or not. And that's the tantalizing possibility. Sometimes invention precedes understanding. The Baghdad Battery might not have powered ancient cities, but it forces us to wonder how many other accidental discoveries from the past have we yet to recognize. Lost between the cracks of history, these jars whisper a challenge to our assumptions. Whether they were tools, ritual objects, or something stranger, they remind us that the line between myth and science is often thinner than we think. And in that ambiguity lies their true power, not just as relics, but as riddles waiting to be solved. Long before modern hospitals or pharmaceutical labs, ancient India developed a medical system so comprehensive it mapped the human body with startling precision, not just in terms of anatomy, but as a web of energies, elements, and interconnected systems. Ayurveda, meaning the science of life, emerged over 3,000 years ago, blending herbal medicine, surgery, and philosophy into a holistic approach that still influences wellness practices today. At its core lies a radical idea. Health isn't just the absence of disease, but a delicate equilibrium between mind, body, and environment. Consider the Sushruta Samhita, a Sanskrit text dating back to 600 BCE, which details surgical procedures that would sound futuristic even centuries later. Sushruta, often called the father of surgery, described techniques for cataract removal, cesarean sections, and even reconstructive rhinoplasty centuries before these practices appeared elsewhere. His tools included finely crafted scalpels, forceps, and needles made of bone or metals, sterilized with herbal infusions to prevent infection. But what's truly remarkable is how these procedures were paired with an understanding of the body's natural rhythms. Patients were prepared with medicated wines to dull pain, and wounds were dressed with antiseptic pastes of honey and turmeric, substances modern science now confirms have potent antibacterial properties. Yet Ayurveda's brilliance extends far beyond scalpels and sutures. Its practitioners classified human constitutions into three doshas: vata, pitta, and kapha, each governing different bodily functions. An imbalance in these energies was thought to cause illness, so treatments focused on restoration rather than suppression. Got a fever? Instead of immediately lowering your temperature, an Ayurvedic healer might prescribe bitter herbs to purge toxins, believing the heat was the body's way of burning off impurities. Chronic inflammation, dietary changes to cool pitta energy, like swapping spicy foods for coconut or cucumber, formed the frontline therapy. This preventative mindset contrasts sharply with modern medicine's tendency to intervene only after symptoms arise. The legacy of these ancient practices is more than historical curiosity. Walk through the streets of Kerala today, and you'll find hospitals where Ayurvedic therapies run alongside Western treatments, offering everything from panchakarma detox rituals to herbal formulations for diabetes. Even the term immune system finds an eerie parallel in Ayurveda's concept of ojas, a vital essence that strengthens resilience. Modern research now validates many of these traditions. Studies show ashwagandha reduces stress hormones, while holy basil fights oxidative damage at a cellular level. But perhaps Ayurveda's most profound lesson is its view of healing as a partnership with nature. Where contemporary medicine often isolates compounds into pills, Ayurvedic remedies preserve the synergy of whole plants, recognizing that a leaf's healing power might lie in the interplay of dozens of active compounds. It's a reminder that sometimes the oldest wisdom holds keys to the future, not in spite of its age, but because of the centuries of observation etched into its foundations. In a world grappling with antibiotic resistance and chronic disease, this 3,000-year-old system whispers an urgent question. What if true health begins not in a lab, but in learning to listen to the body's ancient rhythms? Imagine a world without seismographs, where earthquakes struck without warning, leaving devastation in their wake. Now picture a 2,000-year-old solution, an ornate bronze vessel, ringed with 8 dragon heads, each clutching a metal ball above the open mouth of a waiting toad. This wasn't a ceremonial artifact, it was the world's first earthquake detector, invented by Chinese polymath Zhang Heng in 132 AD, and its design was as elegant as it was ingenious. When the ground shook, the device's hidden mechanism, likely a suspended pendulum inside the vessel, would disrupt one of the dragons, causing it to release its ball into the corresponding toad's mouth. The direction of the fallen ball pointed to the earthquake's epicenter, sometimes hundreds of miles away. Historical records claim it once detected a quake so distant that officials in the capital dismissed the reading until messengers arrived days later confirming tremors in a far-off province. But here's where the debate ignites. No surviving models exist, and scholars still puzzle over how it worked without modern sensors. Some argue the dragons were purely symbolic, their movements triggered by vibrations any observer could feel. Others point to reconstructions suggesting an internal inverted pendulum could indeed sense faint tremors through precise counterweights. The real mystery isn't just its mechanics, but the insight behind it. Zhang Heng theorized that earthquakes were caused by disturbances in cosmic energy, a stark contrast to the mythologies of his era. His device didn't just predict disasters, it reflected a revolutionary belief that natural phenomena could be measured, not just feared. Yet the seismoscope's true legacy might be what it reveals about ancient innovation. While Europe wouldn't develop similar instruments for another 1500 years, Zhang Heng's invention embodied a principle we now take for granted, that hidden forces leave traces, and with the right tools we can decode them. Whether the dragons truly worked or not, they symbolize a leap in human thought, from attributing quakes to angry gods to seeking answers in the language of metal and motion. In that sense, the seismoscope's greatest tremor wasn't in the ground, but in history itself. A reminder that sometimes progress isn't just about what a device does, but the ideas it unleashes, ideas that can ripple across centuries. High above the jungles of Mesoamerica, the Maya gazed at the night sky with an understanding that would eclipse European astronomy for centuries. While medieval scholars still debated whether the Earth was flat, Mayan astronomers had already calculated Venus's 584-day cycle with an error margin of just 2 hours, a precision unmatched until the invention of telescopes. Their celestial observations weren't just academic exercises, they were woven into the very fabric of daily life, dictating when to plant crops, wage wars, or conduct sacred rituals. At the heart of this system lay the Dresden Codex, a bark paper book filled with intricate tables tracking the movements of Venus, Mars, and eclipses. One chart predicts solar eclipses with such accuracy that modern astronomers found its calculations off by only 33 minutes over a 33-year span. How did they achieve this without lenses or metal tools? The answer lies in patience and pattern recognition. Generations of scribes recorded celestial events on towering stone stelae, compiling data that revealed cycles invisible to any single observer. Their long count calendar, spanning over 5,000 years, was so precise it's still used by scholars today to correlate ancient events with our Gregorian system. But the true genius of Mayan astronomy was its fusion of science and spirituality. Venus wasn't just a planet, it was the god Kukulkan, whose appearances signaled times of fortune or famine. When the morning star rose after its period of invisibility, farmers knew the rains would soon follow. Eclipses were moments of cosmic danger, requiring bloodletting rituals to strengthen the sun. This dual view might seem contradictory today, but for the Maya it was seamless. The gods moved the heavens, and by understanding those movements, humans could align themselves with divine order. Compare this to Europe in the same era. While Charlemagne's astronomers struggled to reconcile Ptolemy's outdated models with church doctrine, Mayan cities like Chichen Itza boasted observatories with sightlines aligned to solstices and equinoxes. The Caracol Tower's narrow windows perfectly frame Venus at its most extreme northern and southern positions, evidence of architectural precision serving astronomical purpose. Even their numbering system, with its concept of 0 centuries before Europe adopted it, enabled calculations far beyond medieval capabilities. Yet the most haunting question isn't how they achieved so much, but how much was lost. When Spanish conquistadors burned Mayan libraries in the 16th century, they erased untold volumes of astronomical knowledge. The few surviving codices offer mere glimpses of a system that once rivaled Newton's physics in complexity. Today, archaeologists still debate whether certain temple alignments encode forgotten celestial prophecies or reflect even deeper understandings of time. What remains undeniable is the Maya's legacy as celestial timekeepers. Their achievements force us to reconsider where and when true scientific revolutions occurred. In the shadow of their pyramids, we're left to wonder, if so much was possible with stone tools and naked eyes, what might they have discovered given another millennium of unbroken observation? Buried in the sands near Luxor, a 3,000-year-old wooden toe tells a story that rewrites our understanding of ancient medicine. discovered attached to the mummy of a noblewoman named Tabaketen Mut. This intricate prosthesis isn't some ceremonial ornament, it's a shockingly functional device, complete with hinged joints and wearable straps that suggest it was crafted for daily use. Unlike the crude peg legs of medieval Europe, this artifact reveals an astonishing level of anatomical insight. The curvature matches a real toe's motion, allowing the wearer to walk naturally in sandals, while the leather binding shows wear patterns proving it wasn't just for burial rituals. This wasn't medicine as superstition, it was practical engineering born from empathy. What's truly groundbreaking is what the toe implies about Egyptian society. Prosthetics require more than technical skill, they demand a cultural willingness to invest in quality of life for those with disabilities. Medical texts from the era describe detailed treatments for fractures and wounds, but this physical evidence goes further. The toe's owner, likely a priest's daughter who lost her digit to diabetes or infection, would have faced immense social stigma in many ancient cultures. Yet her prosthesis, delicately carved from cartonnage and tinted to match her skin tone, speaks of a civilization that valued mobility and dignity. Modern CT scans reveal something even more remarkable. The device was refitted multiple times over years, suggesting follow-up care akin to today's prosthetic adjustments. Compare this to Europe's Dark Ages, where amputees were often left to hobble on crutches, and the sophistication becomes even more striking. Egyptian physicians understood weight distribution. The toe's angled base prevented pressure sores and used materials that balanced flexibility with durability. Recent tests with replicas on volunteer amputees confirmed its functionality, whereas reported surprising comfort walking on sandy terrain, a testament to its design. But perhaps the most poignant detail lies in the inscriptions found near Tabaketen Mut's tomb, invoking prayers for her complete journey into the afterlife. In a culture obsessed with physical wholeness for resurrection, this prosthetic wasn't just a tool, it was a bridge between worlds, ensuring she'd stride perfected into eternity. Yet the mystery lingers. How many other such innovations were lost to time? This lone surviving toe hints at a broader tradition of assistive devices, one that challenges our assumptions about ancient priorities. While we marvel at pyramids and golden masks, this humble artifact whispers a different truth: that greatness isn't just measured in monuments, but in how a society cares for its most vulnerable. 3 millennia later, as we debate medical ethics and accessibility, the Egyptians left us an unexpected lesson. True advancement isn't about conquering nature, but about helping each other move through the world with grace. High in the Andes, where thin air twists perception and survival demands resilience, the Inca developed a medical practice that would make modern surgeons pause drilling holes into living skulls with astonishing precision. Trepanation, the ancient art of removing sections of bone from the cranium, wasn't some ritualistic gamble. It was a calculated response to trauma, epilepsy, or even spiritual maladies. Archaeologists have uncovered hundreds of trep and skulls across Peru, many showing clear signs of healing, proof that patients not only survived the procedure but thrived afterward. The survival rate, nearly 80% in some regions, a staggering statistic considering this was done without anesthesia, antibiotics, or sterile instruments. The tools themselves were deceptively simple: obsidian blades sharper than modern steel, bronze tumis, ritual knives, and hand-operated drills made of bone or copper. Surgeons would scrape or bore into the skull, carefully avoiding the delicate membranes beneath. Some skulls reveal multiple trepanations, suggesting repeat procedures on the same individual, a testament to both the patient's trust and the surgeon's skill. What's even more remarkable is how they adapted their techniques. Early methods involved cutting square grooves, but over centuries, Inca medics refined their approach to circular holes, which minimized stress fractures and improved recovery rates. Compare this to medieval Europe, where healing often meant bloodletting or prayers. While Western medicine struggled with basic anatomy, Inca surgeons mapped the skull's vulnerabilities through trial and observation. They understood that pressure from head trauma needed release, predating modern neurosurgery's use of decompressive craniotomies by nearly 1,000 years. Some trepan skulls even show evidence of gold plates inserted to protect the brain, an early form of cranial reconstruction. Yet the true genius of Inca trepanation lies in its holistic approach. Unlike today's sterile operating rooms, these procedures were likely performed in open air, with herbal antiseptics like coca leaves or chicha beer numbing the pain. Shamans might have chanted incantations not just as superstition, but to stabilize the patient's psyche, a primitive parallel to modern medicine's recognition of mental state affecting recovery. The healed bone growth on these skulls tells a silent story. Communities that valued life enough to develop sophisticated interventions, and patients willing to endure unimaginable pain for a chance at healing. So why did this knowledge vanish? The Spanish conquest didn't just topple empires, it erased medical traditions, dismissing indigenous practices as pagan ignorance. Yet the skulls remain silent witnesses to a time when science and spirituality weren't opposites, but partners in unraveling the body's mysteries. As modern surgeons now explore the benefits of mindfulness in recovery, we're left to wonder, did the Inca, in their own way, grasp truths we're only beginning to rediscover? Deep in the clay archives of ancient Mesopotamia, a cracked tablet no larger than your hand holds secrets that rewrite mathematical history. Known as Plimpton 322, this 4,000-year-old Babylonian artifact doesn't just record simple arithmetic, it catalogs Pythagorean triples with stunning accuracy, a full millennium before Pythagoras was even born. But here's what makes it extraordinary. The tablet isn't merely a list of numbers. It's a systematic table of what we now call Pythagorean triples, sets of 3 whole numbers that perfectly fit the equation a squared plus b squared equals c squared, the foundation of right-angled triangles. The precision is breathtaking. One entry reads 1159, 2890, and 3201. Plug these into the Pythagorean theorem, and the math holds down to the last digit. The Babylonians achieved this without algebra as we know it, using a base 60 numeral system that gave them remarkable computational flexibility. Unlike our base 10 system, base 60 allowed for cleaner divisions, which is why we still use it today when measuring time 60 seconds in a minute and angles 360 degrees in a circle. But the real mystery isn't how they calculated these values, it's why. Some scholars argue Plimpton 322 was a teacher's aid, a collection of practice problems for scribble students learning advanced mathematics. The tablet's left edge is broken, but surviving text hints at step-by-step instructions, suggesting an educational purpose. Others propose something far more revolutionary, that Babylonian surveyors or architects used these tables for real-world applications, perhaps calculating land boundaries or constructing temple dimensions with geometric precision. The debate hinges on one tantalizing detail. The triples aren't arranged randomly, they follow a consistent pattern, sorted by the ratio of the short to long side of each triangle in descending order. This structure implies an intentional, possibly even theoretical approach to mathematics, not just rote record-keeping. Could the Babylonians have understood principles of trigonometry long before Hipparchus, the Greek astronomer credited with its invention? Modern reconstructions show that with this tablet, they could have calculated angles accurate to within a fraction of a degree, a feat that would have been invaluable for astronomy or engineering. Yet the most humbling aspect of Plimpton 322 isn't its sophistication, it's how narrowly it survived. Unearthed in the early 20th century near Baghdad, the tablet was nearly discarded as mundane debris before scholars recognized its significance. Thousands of similar tablets likely crumbled to dust or remain buried, their knowledge lost forever. This single relic forces us to reconsider the timeline of mathematical discovery. proving that theoretical brilliance wasn't confined to classical Greece. So the next time you glance at a clock or measure an angle, remember, those numbers whisper across millennia, a testament to minds who saw the universe not in chaos, but in patterns waiting to be decoded. The Babylonians may have left no grand treatises or famous theorems, but in the grooves of this fragile clay, they etched a truth we're only beginning to fully grasp: that mathematics isn't invented but discovered, its truths echoing long after their discoverers fade into history. 2,000 years before the Industrial Revolution, a brilliant mind in Alexandria dreamed of harnessing steam's power, and then built it. Hero of Alexandria's Eolipile wasn't just a curiosity. It was the world's first steam engine, a spinning bronze sphere perched on pipes that hissed with the energy of boiling water. Here's how it worked. Fill a sealed cauldron with water, heat it over a flame, and watch as steam shot through two bent nozzles on the sphere's sides. The force of the escaping vapor set the entire device whirling at dizzying speeds, a primitive yet functional turbine that converted heat into motion. In essence, Hero had unlocked the basic principle behind every steam engine that would later power factories, trains, and ships, except his invention remained a party trick, showcased to dazzle temple visitors rather than reshape civilizations. The reasons it never industrialized reveal as much about ancient society as the device itself. Unlike James Watt's 18th century steam engine, which was designed to pump water from coal mines, the Eolipile had no practical application in a world where slave labor was abundant and cheap. The Greeks saw it as a marvel of pneumatics, a demonstration of nature's hidden forces, but not as a tool to replace human toil. There was also the matter of materials. Hero's bronze contraption couldn't withstand high pressures for extended periods, lacking the iron alloys and precision valves that later engineers would develop. And perhaps most crucially, the intellectual climate of the time prioritized philosophy over mechanical innovation. While Archimedes famously said, "Give me a lever and I shall move the world," Greek thinkers were more interested in understanding principles than scaling them into world-changing technology. Now imagine an alternate history where Hero's invention sparked an industrial revolution in the 1st century. Picture Alexandria's docks bustling with steam-powered cranes, or Roman mines employing piston-driven pumps to unearth deeper ore deposits. The ripple effects would have been staggering: faster communication, expanded trade networks, even early mechanized agriculture. The Roman Empire, with its vast infrastructure and appetite for engineering, might have clung to power for centuries longer, delaying the Dark Ages. But reality took a different path. Hero's manuscript survived, influencing Islamic scholars and Renaissance thinkers. Yet the Eolipile itself faded into obscurity, a tantalizing what-if of technological history. What makes the Eolipile so haunting isn't just its squandered potential, but what it says about how societies adopt innovation. Breakthroughs don't spread in a vacuum. They need the right economic, cultural, and material conditions to take root. Hero had the genius to see steam's power, but his world lacked the pressures, both literal and societal, to turn that vision into revolution. It's a reminder that progress isn't linear, and that even the brightest sparks sometimes flicker out, waiting for the right moment to ignite. Standing in the ruins of Mohenjo-Daro, you'd be forgiven for thinking you'd stumbled upon the blueprints of a modern metropolis, except this city thrived over 4,000 years ago. The Indus Valley civilization didn't just build homes, they engineered an urban masterpiece with grid-patterned streets aligned to cardinal directions, a sewage network that put medieval Europe to shame, and bricks so standardized their dimensions varied by less than a centimeter across the entire city. Every detail, from the orientation of neighborhoods to the placement of wells, reflected a level of civic planning unmatched until the rise of Rome. Take their drainage systems. Covered channels ran beneath streets, filtering waste away from residences and into designated disposal areas. Each house connected to this network through precisely sloped pipes that prevented backflow, a feature some developing cities still lack today. Then there's the Great Bath, a massive public pool lined with watertight bitumen and fed by an elaborate system of drains and freshwater inlets. Unlike Roman baths built for leisure, this structure likely served ritual purposes, hinting at a society where spirituality and urban functionality intertwined seamlessly. But what's truly staggering is the absence of coercion. Unlike Egypt's pyramid builders or Mesopotamia's ziggurat laborers, the people of Mohenjo-Daro showed no signs of being driven by a despotic ruler. Archaeologists find no grand palaces or royal tombs, just uniform housing, communal grain stores, and public infrastructure suggesting collective decision-making. Even their weights and measures followed strict uniformity across hundreds of miles of territory, implying a shared system of trade and governance without centralized domination. So why did such an advanced civilization vanish? Theories range from climate shifts drying up the Saraswati River to invasions by nomadic tribes, but the truth may be more complex. Soil samples reveal prolonged flooding that could have disrupted agriculture, while skeletal remains show signs of malnutrition in the city's final years. Yet, unlike other fallen empires, the Indus Valley left no evidence of war or collapse, just a gradual abandonment, as if the people simply walked away from their engineered perfection. Perhaps their greatest lesson isn't in how they built, but in how they coexisted. In an era when most cultures erected monuments to gods and kings, Mohenjo-Daro's legacy lies in its gutters and bricks, proof that brilliance can flourish without tyranny, and that the most enduring innovations aren't always the grandest, but the ones that serve everyone equally. As modern cities grapple with inequality and crumbling infrastructure, these ancient planners whisper a provocative question. What if progress isn't measured in height but in depth, in the unseen systems that sustain a society long after its monuments fade? Imagine sailing across the North Atlantic under thick, sunless skies, no compass, no landmarks, just an endless expanse of gray waves. For Viking navigators, this wasn't a nightmare scenario, it was routine. Their secret, a mysterious tool mentioned in sagas as a sunstone, a crystal that could reveal the sun's position even when clouds obscured it entirely. For centuries, historians dismissed these accounts as myth until modern science uncovered the startling truth behind the legends. These weren't just pretty rocks. Researchers now believe Vikings used calcite crystals, a transparent mineral that polarizes light. When held toward the sky and rotated, certain types of calcite split sunlight into dual beams. By turning the stone until both beams matched in brightness, navigators could pinpoint the sun's location with eerie accuracy, even during twilight or heavy overcast. In 2008, a team tested this theory on replica Viking ships, using nothing but a calcite sunstone and historical sailing methods. The result: they navigated within 1% of modern GPS coordinates, proving these crystals weren't just plausible, they were precision instruments. The implications rewrite our understanding of Viking expansion. While medieval Europe clung to coastlines, fearing the open ocean, Norse ships crossed thousands of miles to Iceland, Greenland, and even North America. Their mastery of the North Atlantic wasn't just brute courage, it was cutting-edge technology disguised as folklore. Sunstones allowed them to sail earlier and later in the season than competitors, avoiding storms and ice that doomed others. But here's the twist: no intact sunstones have ever been found on Viking sites. The evidence lies in shards of calcite discovered aboard wrecks alongside sagas describing their use. Some skeptics argue they might have relied more on wave patterns or bird behavior, yet experimental archaeology keeps tilting the scales. In 2011, a study showed that under Arctic haze conditions, sunstone navigation could outperform magnetic compasses which falter near the poles. What's most inspiring isn't just the Vikings' ingenuity, but their ability to merge observation with innovation. They didn't understand light polarization as we do. They simply noticed patterns and harnessed them. In an era where we take satellite navigation for granted, these ancient mariners remind us that sometimes the sharpest tools aren't the most complex, but the ones that listen closest to nature's whispers. Their sunstones didn't just guide ships, they lit the way for a scientific mindset hidden in plain sight, wrapped in the poetry of sagas. In the scorching deserts of ancient Persia, where summer temperatures could melt stone, engineers perfected a technology that seems almost impossible: harvesting and storing ice year-round. The yakchul, meaning ice pit, wasn't just a primitive cellar. It was a masterpiece of passive cooling, standing as tall as a two-story building with walls thick enough to shield its precious contents from the relentless sun. These domed structures dotted the arid landscape, providing chilled water and preserved food to cities in climates where ice should have been unthinkable. The secret lay in their ingenious design. Yakchuls used wind catchers, towering vents that funneled breezes down into underground chambers, where the air passed over Qanat's subterranean water channels fed by mountain snowmelt. As the wind evaporated moisture from these channels, the surrounding temperature plummeted, sometimes dropping below freezing even in midsummer. Workers would pour water into shallow pools at night, letting the rapid evaporation and radiative cooling freeze it into thin layers of ice by dawn. This ice was then packed with insulating layers of straw and salt, stored in the yakchul's central pit, where the thick mud brick walls and shade-producing exterior kept it solid for months. Modern engineers marvel at the efficiency of these systems. The domed shape minimized surface area exposed to sunlight, while the wind catchers operated without moving parts, relying solely on convection. Some yakchuls could maintain near-freezing temperatures even when outside air soared above 100 degrees, a feat that rivals today's most advanced passive cooling designs. In fact, contemporary architects studying these structures have adapted their principles for eco-friendly buildings, using underground thermal mass and wind-driven ventilation to reduce reliance on air conditioning. But what's most striking is how these ancient coolers reflect a profound understanding of microclimates. Persian builders didn't just fight the desert's heat, they collaborated with it, harnessing dry winds and starry night skies as tools rather than obstacles. Compare this to modern refrigeration, which consumes vast energy to brute force temperature control, and the yakchul stands as a quiet provocation. Sometimes the most advanced solutions aren't about overpowering nature but listening to it. Yet for all their brilliance, these ice houses nearly vanished from history. With the rise of electric refrigeration in the 20th century, many yakchuls crumbled into ruins, their techniques forgotten. Only recently have researchers begun piecing together their secrets, often relying on centuries-old manuscripts and the fading memories of village elders. A handful of restored yakchuls still stand in Iran today, silent, dome-shaped monuments to an era when sustainability wasn't a buzzword, but a necessity carved from mud and wind. Perhaps their greatest legacy isn't just in the ice they stored, but in the philosophy they embodied. In a world grappling with energy crises, these ancient towers whisper a radical idea: that true innovation doesn't always mean inventing something new, but remembering what we've lost. Long before telescopes pierced the night sky, Aboriginal Australians were mapping the cosmos with nothing but memory and song. For over 65,000 years, making theirs the oldest continuous culture on Earth, they tracked celestial movements with a precision that modern astronomy has only recently confirmed. Take Eta Carinii, a volatile star system 16,000 light-years away that erupts unpredictably. In the 19th century, European astronomers recorded its sudden brightening as a new discovery. Yet Aboriginal oral traditions had already described its past explosions in meticulous detail, preserved through generations in songlines, melodic maps that encode celestial knowledge within stories of the dreaming. These weren't just casual observations. Songlines functioned as both navigation charts and astronomical records, with landmarks and star positions woven together in rhythmic sequences. A single song might describe the path of the Milky Way across the seasons while also serving as a guide across hundreds of miles of desert. The Wardaman people, for instance, called Eta Carinae Jinnah, placing it at the center of a cosmic emu's egg in their mythology. When the star flared in the 1800s, their songs interpreted it as the egg cracking open, a poetic description matching the violent stellar outburst modern astronomers now study with satellites. What's truly staggering is the timescale of this knowledge. Some Aboriginal traditions reference stars that died millennia ago, their light only now fading from view. The Borong people's stories include a lost star that correlates with the Vela supernova remnant, a cosmic explosion witnessed 12,000 years ago. How could oral histories retain such detail across hundreds of generations? The answer lies in the strict teaching methods of Aboriginal elders. Astronomical knowledge wasn't casually shared. It was passed down through rigorous ceremony, with each nuance of pitch and rhythm acting as a mnemonic device. A single mispronounced word could distort celestial coordinates, so apprentices trained for decades to become living libraries. Modern science is only beginning to grasp the depth of this system. In 2016, researchers published a study comparing Aboriginal star knowledge with telescopic data, finding consistent accuracy in observations of meteor showers, planetary movements, and even the shifting positions of stars due to Earth's axial precession, a phenomenon first quantified by the Greeks 2,000 years ago. But where Greek astronomers wrote on papyrus, Aboriginal custodians encoded the same understanding in dance, art, and song. The difference speaks volumes. One culture preserved knowledge on perishable scrolls, the other etched it into the collective memory of a people. Yet for all its sophistication, this astronomical tradition teetered on the brink of extinction. Colonization disrupted songlines, and with them, millennia of unbroken observation. Today, elders work with astrophysicists to reconstruct fragments of this knowledge, like piecing together a shattered telescope lens. The collaboration has revealed unexpected synergies. Aboriginal descriptions of star clouds now help astronomers locate dark matter, while ancient warnings about certain bright stars align with newly discovered gamma-ray sources. In the end, these songlines challenge our very definition of science. Without equations or instruments, Aboriginal Australians achieved a mastery of the night sky that rivaled any observatory. Their legacy whispers a profound truth, that curiosity isn't bound by technology, and that the universe reveals its secrets to those who learn to listen not just with instruments, but with stories that outlast civilizations. Centuries before sailors relied on compasses to cross uncharted oceans, Chinese diviners were using magnetic stones to harmonize the unseen energies of the world. The earliest compasses weren't navigation tools at all. They were spiritual instruments shaped like spoons and carved from lodestone, a naturally magnetic mineral. These south-pointing spoons rested on polished bronze plates, their handles swinging unerringly toward magnetic south, not by accident, but because ancient scholars believed aligning spaces with Earth's invisible forces brought balance and good fortune. This was Feng Shui in its purest form, a practice where geography met cosmology and magnetism held the key to cosmic order. The transition from mystical tool to seafaring essential began during the Han Dynasty around 200 BC. Scholars noticed that when lodestone needles were floated on water or suspended from silk threads, they consistently pointed north-south. At first, this discovery was tucked into imperial manuals as a curiosity, until someone realized its staggering potential for trade. By the 9th century, Chinese navigators were mounting magnetized needles on wooden fish floated in bowls of water, creating the first marine compasses. Suddenly, ships could venture beyond sight of land, even under clouded skies, their course set by an invisible force pulling at a sliver of metal. What's often overlooked is how this humble invention rewrote global economics. With reliable navigation, the Song dynasty's merchant fleets expanded trade routes to Arabia and East Africa, carrying porcelain, silk, and gunpowder to distant markets. The compass didn't just guide ships, it fueled the first wave of globalization, knitting together continents in a web of commerce. Arab traders eventually adopted the technology, passing it to Europeans during the Crusades, where it catalyzed the age of exploration. Columbus, Magellan, and Zheng He all owed their voyages to a principle discovered by Chinese scholars seeking harmony between earth and sky. Yet the compass's dual legacy, as both spiritual tool and scientific instrument, reveals a deeper truth about ancient innovation. The same culture that perfected magnetic navigation also revered it as a bridge between realms. Emperors used compasses to orient palaces and tombs, believing proper alignment ensured dynastic longevity. Even today, traditional Feng Shui masters employ Luopan compasses, their concentric rings mapping not just directions but the flow of Qi energy. In a world that often divorces science from symbolism, the compass stands as a reminder that some discoveries resonate far beyond their practical use. They shape how we see our place in the cosmos. Perhaps the most poignant twist is how modern science has circled back to the compass's roots. Geophysicists now study Earth's shifting magnetic field, which guided those early lodestone spoons to understand planetary core dynamics. The same force that once aligned temples now helps predict solar storms threatening satellites. From divination to deep space navigation, the journey of this ancient tool proves that sometimes the most profound technologies begin not with utility but with wonder. Hidden among the medical papyri of ancient Egypt lies a test for pregnancy so ingenious, it wouldn't be scientifically validated until the 20th century. The Berlin Papyrus, dating back to 1300 BC, contains instructions that sound more like farming advice than gynecology. A woman suspected of pregnancy should urinate on bags of barley and wheat seeds over several days. If the barley sprouted, the text claimed she was carrying a boy. If the wheat grew, a girl. And if neither germinated, she wasn't pregnant at all. For centuries, modern scholars dismissed this as mere folklore until laboratory experiments revealed the shocking truth. The secret lies in plant hormones. Estrogen, a key pregnancy hormone found in urine, stimulates seed germination at certain concentrations. In 1963, researchers decided to put the ancient method to the test. They found that urine from pregnant women caused barley seeds to sprout 70% of the time, while non-pregnant urine showed no effect. The gender prediction proved less reliable, but the core principle was sound. Egyptian physicians had stumbled onto a bioassay thousands of years before the term existed. Even more remarkably, their barley test predates the earliest known European pregnancy tests by over 3 millennia. Those relied on absurdities like injecting urine into frogs and watching for egg production. What's striking isn't just the accuracy, but the observational rigor behind it. This wasn't guesswork, it was repeatable experimentation. The Egyptians likely noticed patterns over generations. Perhaps midwives observed that certain women's urine made temple offerings of grain sprout unexpectedly. Their method even accounted for false negatives. The papyrus specifies morning urine, which we now know has higher hormone concentrations. Modern home pregnancy tests work on a similar principle, detecting human chorionic gonadotropin (HCG) in urine, a hormone the barley and wheat responded to indirectly through shared growth pathways. Yet the real marvel is how this knowledge was preserved. While Greek and Roman medical texts were copied and recopied, Egypt's papyri survived by sheer accident of climate, dry sands protecting fragile scrolls that might have otherwise crumbled away. The Berlin Papyrus itself was nearly discarded as rubbish before a sharp-eyed Egyptologist recognized its value in the late 19th century. Today, it sits in a climate-controlled museum case, a fragile testament to how much we still don't know about ancient science. Perhaps the most humbling thought isn't that they got it right, but how close we came to never knowing they'd tried at all. In a world without microscopes or biochemistry, the Egyptians harnessed biology's subtle cues with quiet brilliance. Their test required no expensive equipment, just seeds, observation, and a deep understanding of nature's interconnectedness, a reminder that sometimes the oldest answers are waiting in the most unexpected places. Buried beneath the ash of Mount Vesuvius, a collection of bronze and iron instruments offers a haunting glimpse into Roman medicine, tools so advanced they wouldn't look out of place in a modern operating room. Among the ruins of Pompeii, archaeologists uncovered scalpels with razor-sharp steel blades, finely toothed bone saws, and delicate forceps with scissor-like hinges. One particularly intricate tool, a bronze uterine dilator, mirrors designs still used in gynecology today. But what's most startling isn't just their precision. It's the realization that Roman surgeons performed procedures ranging from cataract removal to amputations with instruments nearly identical to those of the 19th century. Take the surgical drills. These handheld devices, fitted with interchangeable bits, were used for trepanning skulls or extracting arrowheads. Their corkscrew design allowed controlled penetration, while fluted edges efficiently cleared bone fragments, an engineering solution so effective that similar drills reappeared during the American Civil War. Even the humble scalpel reveals sophistication. Some Pompeian specimens feature folding mechanisms, their blades retracting into ornate handles for portability. This wasn't makeshift medicine, it was a standardized toolkit with variations tailored for specific tissues. Yet the true marvel lies in how they paired these tools with anesthesia. Roman physicians concocted potent sedatives from opium poppies, mandrake root, and even fermented ivy. The famed medic Dioscorides recorded recipes where mandrake wine was administered before surgery, its tropane alkaloids inducing unconsciousness. Sponges soaked in a mixture of vinegar and opium might have been held over patients' noses, mimicking early inhalation anesthesia. Skeletons from Herculaneum show evidence of successful limb amputations, their clean bone cuts suggesting patients didn't thrash during procedures, proof these methods had real efficacy. What's often overlooked is the logistical brilliance behind Roman surgery. Military medics carried sterilizing kits with bronze containers for boiling instruments, while civilian doctors organized tools into layered ivory boxes resembling modern surgical trays. The Romans even pioneered early antiseptics, using vinegar and thyme oil to clean wounds, centuries before germ theory. A first-century fresco from Pompeii's House of the Surgeon depicts a battlefield medic treating a wounded soldier, his toolkit laid out with the same systematic care seen in today's trauma centers. The unsettling question isn't how they achieved so much, but why such knowledge regressed. After Rome's fall, many of these techniques vanished in Europe, replaced by crude practices like cauterizing wounds with hot oil. It took nearly 1,500 years for Western medicine to regain Roman levels of surgical precision. Perhaps their greatest legacy isn't just the tools they forged, but the reminder that progress isn't guaranteed. Sometimes the brightest lights flicker out, waiting to be rediscovered by futures that forgot them. Deep in the sweltering jungles of Mesoamerica, the Olmecs achieved something modern chemists wouldn't replicate until the 19th century. They turned sticky tree sap into bouncy, durable rubber. 3,000 years before Charles Goodyear patented vulcanization, these ancient innovators were already molding rubber into everything from ceremonial balls to waterproof footwear. The secret, a daring blend of science and serendipity, using two ingredients that seemed worlds apart, the milky latex of the rubber tree and the sap of the morning glory vine. The process was deceptively simple yet chemically brilliant. Harvesters would collect latex by slashing diagonal cuts into the bark of Castilla elastica trees, letting the white liquid drip onto wooden paddles. But raw latex is brittle when dry and gooey when warm, useless for the Olmecs' famous ball games, where players hurled heavy rubber spheres weighing up to 8 pounds using only their hips. That's where the morning glory came in. By boiling the vine sap, a juice rich in sulfur compounds, and mixing it with the latex, they triggered a molecular transformation. The sulfur atoms bonded with the latex's polymer chains, creating a cross-linked structure that resisted heat and retained elasticity. In essence, they discovered vulcanization millennia before the term existed. These rubber balls weren't just toys, they were cosmic symbols. The Olmecs saw the game as a ritual reenactment of celestial battles, with the ball representing the sun or moon bouncing between realms. Courts were often aligned with astronomical events, and surviving carvings show players wearing elaborate padding, evidence of a sport so intense it sometimes ended in sacrifice. Modern reconstructions reveal the balls could rebound over 6 feet high, their durability allowing them to withstand the brutal gameplay depicted in murals. What's astonishing is how this technology spread. By the time Spanish conquistadors arrived, rubber was ubiquitous across Mesoamerica. Aztec merchants traded rubber sandals, while Maya artists used it to waterproof textiles. Yet when Europeans first encountered bouncy rubber balls, they dismissed them as exotic curiosities, failing to grasp the chemistry behind them. It took until the 1800s for Western science to reverse engineer what the Olmecs had perfected through observation and experimentation. The real mystery isn't how they made rubber, but why such a revolutionary material remained confined to the region. Unlike bronze or iron, which catalyzed global trade, rubber's potential lay dormant until the Industrial Revolution. Perhaps the answer lies in the Olmecs' worldview. For them, rubber wasn't just a substance, it was sacred, a bridge between earth and sky. In their hands, chemistry wasn't industry, it was ritual, a reminder that some discoveries aren't just about utility, but about understanding the very texture of the world. 2,400 years before the Large Hadron Collider smashed its first protons, a Greek philosopher named Democritus sat by the Aegean Sea, breaking a loaf of bread in half again and again until he couldn't split it further. That moment of contemplation led to one of history's most staggering intellectual leaps, the idea that all matter consists of tiny, indivisible particles he called atomos, meaning uncuttable. While his contemporaries debated whether the world was made of fire, water, or earth, Democritus proposed something radical, that everything, from mountain ranges to human flesh, was just atoms moving through void, combining and separating in infinite configurations. What's astonishing isn't just the theory's prescience, but how closely it mirrors modern quantum physics. Democritus described atoms as differing in shape and size, with hooks and grooves allowing them to interlock. Today, we know carbon atoms form chains, while hydrogen bonds create water's fluidity, exactly the kind of mechanical interactions he envisioned. He even speculated that iron's hardness came from dense, tightly packed atoms, while air's lightness stemmed from sparse, delicate ones. Compare this to Aristotle's opposing view, which dominated Western thought for centuries, that matter derived from 4 abstract elements: earth, air, fire, water, possessing qualities like dryness or coldness. While Aristotle's framework prioritized philosophical elegance, Democritus sought physical explanations, insisting reality could be reduced to tangible, mechanistic parts. The clash between these worldviews shaped scientific history. Aristotle's authority suppressed atomism for nearly 2 millennia, until Renaissance thinkers like Galileo and Newton resurrected it. Yet Democritus' brilliance shines in the gaps he couldn't possibly have filled. He theorized the existence of a vacuum, a concept so controversial that Aristotle famously declared, "Nature abhors it," centuries before Evangelista Torricelli's barometer proved empty space could exist. He even pondered whether other worlds might harbor different atomic arrangements, a precursor to modern multiverse hypotheses. Perhaps the most poignant twist is how close Democritus came to the truth without a single microscope or particle accelerator. His tools were observation and logic. Watching dust motes dance in sunlight, he reasoned their erratic movements revealed invisible atomic collisions. Crushing herbs, he noted how scents traveled, evidence, he thought, of airborne atoms stimulating the nose. These inferences, though simplistic, followed the same deductive process that later guided Dalton and Rutherford. Yet for all its visionary power, ancient atomism lacked one critical element: experimental proof. Without the ability to test his ideas, Democritus' theory remained a philosophical stroke of genius rather than a scientific revolution. That's the tragic beauty of his story. He saw the universe's building blocks clearly, but his world lacked the tools to grasp them. As we peer today into electron microscopes and cloud chambers, we're fulfilling a vision woven into history's fabric by a thinker who trusted his mind's eye over the dogma of his age. In that sense, every quark and neutrino we detect whispers across time, echoing an idea born not in a lab, but on a sunlit Greek shore where a man tearing bread glimpsed the infinite in the infinitesimal. Imagine walking into a Mesopotamian tavern 4,000 years ago, the air thick with the yeasty scent of fermenting grain, clay jars brimming with golden liquid, and workers lining up to collect their daily wages. In beer, this wasn't just a drink, it was the lifeblood of civilization, enshrined in the world's oldest surviving recipe, etched into a cuneiform tablet around 1800 BC. The hymn to Ninkasi, a song dedicated to the goddess of brewing, doubles as step-by-step instructions: malted barley soaked in water, mixed with honey and dates, then left to ferment in large vats. But here's what's wild: modern brewers who have recreated this ancient recipe describe it as surprisingly drinkable, with a cloudy appearance and a tangy, bread-like flavor closer to a hearty kvass than today's crisp lagers. Beer in Mesopotamia wasn't just a beverage, it was currency. Workers building the ziggurats of received beer rations, up to 5 liters a day based on their labor. Archaeologists have uncovered wage tables specifying exactly how much each worker earned, from high-ranking officials down to manual laborers. Even the pyramids of Egypt were built, in part, on a foundation of beer, a staple so vital it was buried with pharaohs for the afterlife. But the Mesopotamians took it further, integrating beer into their cosmology. Ninkasi wasn't just a patron deity, she was a divine chemist, her hymn preserving brewing knowledge as sacred text. The process itself was seen as alchemy, transforming humble grain into something that could unite communities, fuel economies, and commune with the gods. Zoom out, and the real genius lies in how they engineered fermentation without understanding microbiology. Their bapia bread, a twice-baked crumbly loaf, acted as a primitive malt, its starches broken down by saliva enzymes when chewed, a method still used in some traditional South American chicha. The fermentation vessels, often coated with bitumen to prevent leaks, created ideal anaerobic conditions for yeast to thrive. Recent residue analyses of ancient jugs revealed traces of tartaric acid, suggesting they might have even experimented with wild yeast strains long before Louis Pasteur documented fermentation science. Yet for all its sophistication, Mesopotamian beer would baffle modern palates. Unfiltered and packed with sediment, it was consumed through straws to avoid the bitter sludge at the bottom of shared jars. Some varieties were so thick they resembled porridge, requiring straining before drinking. Compare that to today's crystal-clear IPAs or frothy stouts, and it's a stark reminder of how far brewing has come, or perhaps how much we've overcomplicated what began as simple, nourishing sustenance. The legacy of these ancient brewers lingers in every pint glass. Their innovations: temperature control, standardized recipes, even early quality control measures laid the groundwork for a craft we now take for granted. But perhaps their greatest lesson wasn't in the brewing, but in the understanding that some of humanity's deepest connections are forged not in stone or scripture, but in the shared act of raising a drink together. From the mud brick taverns of Sumer to today's microbreweries, beer remains one of our oldest unbroken traditions, a frothy, bubbling thread tying us to the very dawn of civilization. For centuries, Chinese scholars scribbled observations that seemed like superstition, until modern science caught up. In 117-7 AD, imperial records from the Han Dynasty noted a curious event. Days before a devastating quake toppled city walls, rats and snakes fled their nests in unison. Similar accounts piled up over generations: dogs howling at nothing, chickens refusing to roost, even fish leaping from ponds hours before the ground shook. What officials dismissed as peasant folklore turned out to be nature's earliest warning system, meticulously documented in bamboo annals and court diaries. These weren't random coincidences, they were the first glimmers of seismic prediction, recorded 1700 years before Western science acknowledged animal behavior could foreshadow earthquakes. The mechanisms behind these phenomena are now grounded in biology. Animals detect subtle precursors humans miss: infrasound waves below our hearing range, shifts in groundwater chemistry, or even charged particles released by crushing rocks under pressure. In 2005, researchers studying toads noticed they abandoned their breeding grounds days before Italy's L'Aquila earthquake, likely sensing ionic changes in the water. Ancient Chinese observers couldn't explain the physics, but their empirical approach was startlingly methodical. The Zhangheng seismoscope wasn't an isolated marvel, it existed within a broader tradition of correlating anomalies with disasters. One Tang Dynasty text advised officials to track sky lanterns, or mysterious lights now linked to earthquake-induced electrical disturbances, while another manual listed 26 specific animal behaviors tied to impending tremors. Fast forward to today, and these ancient insights are fueling cutting-edge research. China's Haicheng earthquake of 1975 was successfully predicted, evacuating 90,000 people based partly on erratic animal reports. Japan's early warning system now incorporates groundwater monitoring, a direct descendant of Song Dynasty records linking well fluctuations to quakes. Even NASA studies suggest animals sense airborne positive ions released by tectonic stress, a theory that aligns perfectly with Ming-era accounts of restless birds before the Earth groans. Yet the real lesson isn't just in the predictions, it's in the humility of observation. Modern seismology often relies on expensive technology, but these ancient chroniclers worked with patience and attention, spotting patterns invisible to instruments. Their legacy challenges us to widen our toolkit, blending silicon sensors with biological barometers. As cities today install AI-driven warning networks, they're unknowingly echoing a philosophy carved into oracle bones millennia ago. Sometimes the most advanced system isn't the one that shouts loudest, but the one that listens closest to the whispers of the natural world. Beneath the linen wrappings of an Egyptian mummy lies a secret that kept decomposition at bay for thousands of years, not magic but groundbreaking chemistry. The key ingredient wasn't some mythical elixir, but ordinary-looking salts harvested from dry lake beds: natron, a mix of sodium carbonate, sodium bicarbonate, and trace minerals. At first glance, it might resemble modern table salt, but its effects were transformative. When embalmers packed bodies with this desiccating powder, it drew out moisture so completely that bacteria couldn't survive, halting decay in its tracks. Yet natron was just the opening act in a preservation process so sophisticated, modern scientists are still deciphering its secrets. The real revelation came when researchers analyzed the blackened resin pooled in mummified ribcage and skulls. Far from being simple ritualistic adornments, these sticky substances were molecular fortresses against decay. Pine resin, when heated and mixed with beeswax and plant oils, formed a sealant that repelled insects and microbes alike. Recent gas chromatography tests on Tutankhamun's mummy revealed traces of antifungal cedar oil and antibacterial juniper extract, ingredients modern mortuary science now confirms can inhibit mold and flesh-eating bacteria. The Egyptians might not have understood germ theory, but their trial and error formulations achieved what centuries later cultures couldn't: near-perfect preservation without refrigeration or synthetic chemicals. What's most startling is how these techniques evolved through accidental discoveries. Archaeologists suspect the use of natron began when early burials in desert pits naturally dehydrated bodies, inspiring intentional replication. Resin applications likely originated from observing how tree sap protected wounds from infection, a principle later refined into embalming unguents. Even the famous mummy brown pigment used by Renaissance artists made from ground-up mummies unwittingly proved the longevity of these methods when centuries-old tissue fragments retained their structure in oil paints. But the crowning achievement was the embalmers' understanding of timed chemical reactions. They didn't just dump natron on corpses, they adjusted salt mixtures based on climate and body size, leaving tissues submerged for precisely 40 days to avoid over-drying. Too little exposure left organs prone to rot, while too much turned skin brittle. Some mummies show evidence of temporary stuffing, with linen pads soaked in Nile water during processing, a rehydration step that prevented cracking before final wrapping. This level of nuance rivals modern forensic preservation techniques, where pathologists carefully control humidity to maintain tissue integrity. Yet for all their mastery, the Egyptians' knowledge wasn't infallible. Early mummies from the Old Kingdom often deteriorated due to imperfect resin coverage, while New Kingdom embalmers occasionally overused bitumen, turning specimens into brittle, tar-blackened statues. These mistakes are ironically what help Egyptologists trace the science's evolution, revealing a millennia-long process of refinement. Modern experiments replicating these methods have produced startling results. When researchers mummified donated cadavers using authentic techniques, the samples showed significantly less bacterial growth after 6 months than conventionally embalmed bodies. The haunting beauty of this ancient science lies in its duality, equal parts spiritual ritual and biochemical breakthrough. Every linen strip soaked in resin was both a barrier against decay and a metaphysical shield for the soul's journey. In preserving flesh, they believed they were safeguarding eternity itself. As we today grapple with preserving vaccines and food supplies, their legacy whispers a provocative idea: that some of history's most enduring advances spring not from understanding why something works, but from relentless observation of the fact that it does. Deep in the humid jungles where jaguars prowl and howler monkeys shriek, the Maya didn't just consume chocolate. They built an empire on it. Cacao beans, small enough to fit in your palm, became the golden coins of Mesoamerica, trading hands for everything from turquoise jewelry to enslaved laborers. This wasn't casual barter, it was a formalized economic system where 10 beans could buy a rabbit, 100 might secure a canoe, and counterfeiters risked their lives for attempting to pass off carved clay beans as the real thing. The irony: while Europeans were still weighing lumps of silver, Maya merchants had already perfected a lightweight, portable currency that doubled as a coveted luxury, one that could literally be melted down and drunk by the elite. Chocolate's journey from sacred elixir to hard currency reveals just how deeply it was woven into Maya life. Royals sipped frothy cacao drinks spiced with chili and vanilla during coronations, believing the bitter brew connected them to the gods. Temples displayed cacao pods in carvings as symbols of abundance, and hieroglyphs record that victorious warriors demanded tribute in sacks of beans. But what made cacao the ideal money? The answer lies in biology and geography. Cacao trees thrived only in specific microclimates, making the beans scarce enough to hold value, yet durable enough to store for years without spoiling. Unlike grain or feathers, they were nearly impossible to replicate fraudulently. Each bean's unique texture and aroma acted as a built-in anti-counterfeiting measure. The Maya didn't just use cacao for petty trade. Excavations at Tikal uncovered vaults stuffed with beans, suggesting centralized storage akin to modern banks. Spanish chroniclers later documented Aztec tax collectors demanding payments in cacao, a system inherited from Maya predecessors. One account describes a single Maya province delivering 80,000 loads of beans annually, enough to fill multiple cargo ships. The beans even crossed cultural borders. They've been found in ceremonial caches as far north as New Mexico, traded by merchants who recognized their universal appeal. Yet the true brilliance of chocolate money wasn't just its utility, but its dual identity. While gold languished in vaults, cacao circulated endlessly, consumed at festivals, offered to deities, then replenished through harvests. This fluidity between sacred and commercial made it far more than currency. It was a cultural lifeline. When invaders finally toppled Maya cities, they missed the real treasure hidden in plain sight. Not just beans, but the idea that value could grow on trees, ferment in pods, and foam in cups, a system where wealth wasn't hoarded but shared, sip by intoxicating sip. Standing silently in Delhi's Qut complex, a 7-ton iron pillar has baffled scientists for centuries. While modern steel structures crumble within decades under monsoon rains and pollution, this 1,600-year-old monument hasn't rusted, not even a flake. The secret lies not in some mystical coating, but in the very composition of its metal. Crafted during the Gupta Empire around 400 CE, the pillar contains an unusually high phosphorus content, nearly 1% compared to modern steel's mere fraction of that amount. This seemingly minor difference triggers a remarkable chemical reaction. Instead of forming loose, flaky rust, the iron develops a thin, invisible layer of iron hydrogen phosphate that clings tightly to the surface, shielding the metal beneath like an eternal suit of armor. What's truly astonishing isn't just the pillar's durability, but the precision behind its creation. Ancient Indian metallurgists, known as Lohavanaja, smelted iron ores with charcoal and specific mineral additives in clay furnaces, reaching temperatures over 1,200 degrees Celsius. Through trial and observation, they seemingly identified that phosphorus, usually considered an impurity in modern metallurgy, could act as a preservative when balanced just right. The pillar's inscription hints at this knowledge, praising King Chandragupta's reign for producing unconquerable iron weapons. Recent spectroscopic analysis reveals even subtler genius. The metal's low sulfur and magnesium content further inhibits corrosion, while its crystalline structure distributes stress evenly, preventing microcracks that typically invite rust. The burning question isn't how the pillar resists decay, but why. Was this phosphorus-rich alloy a deliberate innovation or a happy accident of local ore composition? Skeptics point out that other artifacts from the same era show corrosion, suggesting inconsistent technique. Yet the Rasaratna Samakaya, a 5th century Sanskrit text, describes precise iron purification methods and mentions alloys that defy time's teeth, a possible reference to anti-corrosion formulas. Compellingly, the pillar's location near an ancient Vishnu temple aligns with Hindu cosmology's emphasis on eternal, unchanging materials for sacred structures. Perhaps the answer lies somewhere between science and spirituality, a blend of empirical discovery and ritual intention that modern analysis struggles to disentangle. Compare this to modern stainless steel, invented only in 1913 after decades of laboratory experiments. Our best alloys rely on chromium to form protective oxide layers, a solution the Gupta metalsmiths seemingly preempted by over a millennium. Even today, metallurgists study the pillar's microstructure to inspire new anti-corrosion coatings for ships and bridges. Yet the pillar's real lesson might be ecological. Its longevity stems partly from being hand-forged in small batches, a stark contrast to today's mass-produced steel, where efficiency often trumps endurance. As skyscrapers built in the 1970s already require costly repairs, this ancient sentinel stands as a silent rebuke, a proof that some technologies don't progress in straight lines, but in loops, returning us to wisdom we forgot we ever knew. When you step into the ruins of a Roman villa, your feet might brush over something the ancient engineers hid beneath the tiles, a heating system so effective it puts many modern homes to shame. The hypocaust was more than just a luxury for the elite. It was a stroke of thermal genius that transformed living spaces across the empire. Imagine a raised floor supported by hundreds of small brick pillars, creating a hollow cavity beneath. Below that, a furnace roared, channeling hot air through the gaps, while flues built into the walls carried warmth upward, ensuring every room stayed toasty even in winter. This wasn't just comfort, it was physics mastered 2,000 years before central heating became commonplace. What made the hypocaust revolutionary wasn't just its design, but its adaptability. From the colossal baths of Caracalla in Rome to modest British villas, the system scaled effortlessly. Engineers adjusted the height of the floor pillars to control heat intensity, shorter pillars for gentle warmth in bedrooms, taller ones for blistering temperatures in coldariums where bathers lounged in steam. The Romans even insulated walls with hollow terracotta tubes called tubuli, trapping heat like a thermal blanket. Modern tests show these structures could maintain rooms at a steady 80 degrees Fahrenheit for hours using only wood or charcoal, all without a single electric pump or thermostat. The real marvel, though, lies in how little the underlying principle has changed. Today's radiant floor heating systems, pipes of warm water snaking beneath hardwood or tile, are direct descendants of the hypocaust. The Romans simply swapped hot air for hot water in some advanced installations, like the famed hypocaustum aquae in Pompeii's Stabian baths, where bronze pipes circulated heated water. Even their fuel efficiency was ahead of its time. Ash from the furnaces was often recycled into mortar, creating a near-zero waste cycle that sustainability experts today would applaud. Yet the hypocaust's legacy isn't just technical, it's cultural. This technology reshaped daily life, turning public baths into social hubs where citizens of all classes mingled. The system's reliance on slave labor to tend furnaces reminds us that progress often came at a moral cost in antiquity. And when Rome fell, the knowledge didn't vanish completely. Byzantine and Islamic builders adapted the design for hammams and palaces, while medieval European castles recreated cruder versions. By the Renaissance, though, the hypocaust was forgotten in the West, buried under centuries of simpler hearths and fireplaces. The lesson here isn't just about heat, it's about continuity. Those tile floors warmed toes from Syria to Scotland, proving that innovation thrives when shared across borders. As we now fiddle with smart thermostats and geothermal pumps, the hypocaust whispers a reminder: sometimes the oldest ideas hold the warmest truth. High in the Andes, where the thin air carries whispers of a lost empire, bundles of knotted strings dangle like mathematical constellations, the quipus of the Inca. Far more than simple counting tools, these intricate arrays of colored chords encoded everything from census figures to epic poems, tax records to celestial events. Each knot's position, size, and even the direction of its twist held meaning, transforming ordinary cotton and camelid wool into a three-dimensional language as complex as any written script. Yet for all their sophistication, quipus guard their secrets stubbornly. Unlike the Rosetta Stone, which cracked Egyptian hieroglyphs by matching them to Greek, no bilingual key exists to unlock their full story. The genius of quipu mathematics lies in its elegant simplicity. Imagine a main chord dangling subsidiary strings, each knotted in clusters representing units, tens, hundreds, and thousands. A figure like 352 would appear as 3 knots in the hundreds position, 5 in the tens, and 2 single knots, a base 10 system eerily familiar to modern eyes. But this was just the foundation. Colors carried semantic weight. Red strings might denote soldiers, yellow for gold, black for time. Knot types, figure 8, long or braided, could toggle between nouns and verbs. Recent studies even suggest some quipus functioned like binary code, with knot sequences acting as logical operators capable of encoding narratives, not just numbers. Deciphering them, however, is like trying to read a book where every chapter's pages have been scattered to the wind. Spanish chroniclers recorded that quippers could recite entire histories, yet colonial priests burned most as pagan artifacts, leaving only 600 survivors a fractured archive. Modern researchers face a paradox. The very accountants who mastered these chords, the quipucamayos, were so skilled they needed no manuals, passing knowledge orally until the practice faded. Today, breakthroughs come in fragments. In 2017, anthropologist Sabine Heil studied quippers from a remote Peruvian village, discovering that chord ply direction, whether strands were twisted clockwise or counterclockwise, could distinguish allied from enemy clans in census records. What's most tantalizing isn't just the code, but what it reveals about Inca governance. With no wheels or draft animals, their empire stretched 2,500 miles, yet administrators tracked millions of subjects, storehouse inventories, and labor rotations with flawless precision, all through these knotted ledgers. Courier runners called chasquis carried quippers along the empire's highway network, creating what some scholars call the first information superhighway. The system was so trusted that Spanish colonial officials initially relied on quipu keepers to calculate tributes, only realizing too late that some chords secretly recorded hidden populations to avoid overtaxation. The quipu's enduring mystery poses a profound question. Can a civilization's memory survive without paper? These strings defy our bias toward alphabetic writing, proving that cognition isn't bound by ink and parchment. As linguists and mathematicians now collaborate with Andean communities to recover fragments of this knotted lexicon, each decoded chord rewrites history not just of the Inca, but of what it means to invent a language shaped by touch rather than sight. The quipu whispers across centuries, reminding us that some truths aren't written but woven, waiting for hands patient enough to untangle their stories. In the highlands of Tanzania, where the Great Rift Valley carves through the earth, archaeologists unearthed furnaces that rewrote the history of metallurgy. These weren't simple clay ovens, they were advanced smelters capable of reaching temperatures over 1,500 degrees Celsius, a feat European blacksmiths wouldn't achieve for another millennium. The key to their astonishing heat, tall, chimney-like structures packed with iron ore and charcoal, where carefully placed bellows funneled air to supercharge combustion. But the real marvel wasn't just the furnace design, it was what came out of them. African metalworkers didn't just produce crude iron blooms, they mastered carbon steel, a material so strong and flexible it became the backbone of an entire trade network spanning the continent. Examinations of excavated steel tools reveal a level of craftsmanship that defies expectations. Spearheads from the region show consistent carbon content between 0.6 and 1.7%. The ideal range for balancing hardness and durability. These weren't accidental alloys, they were the product of meticulous process control. By alternating layers of iron and carbon-rich organic material like bamboo in the furnace, smelters triggered chemical reactions that infused the metal with carbon molecules at just the right concentration. The resulting steel could hold an edge sharper than bronze while resisting the brittleness of pure iron, a breakthrough that gave farmers, hunters, and warriors tools capable of transforming daily life. The ripple effects of this technology stretched far beyond village workshops. In bustling Swahili coastal cities like Kilwa and Mombasa, Tanzanian steel became a coveted export, traded for Arabian glass and Indian spices. Recent metallurgical analysis of artifacts from Zimbabwe's Great Enclosure matched their composition to Tanzanian ore sources, proving these high-carbon blades traveled over 1,000 miles along ancient trade routes. Even more telling are accounts from 9th century Arab geographer al-Masudi, who marveled at East African swords that could bend without breaking, a clear description of premium steel's flexibility. What's often overlooked is how these innovations emerged independent of Eurasian influence. While Rome and Han China developed their own metallurgical traditions, Tanzanian smelters pioneered techniques tailored to local conditions. Their furnaces used termite mound clay, rich in heat-resistant aluminosilicate minerals, while their bellows designs mimicked the shape of baobab seed pods for optimal airflow. This wasn't borrowed knowledge, it was homegrown genius, proof that scientific progress isn't confined to textbook cradles of civilization. Yet the most haunting question isn't how they achieved such temperatures, but why the practice faded. Unlike European blast furnaces that evolved continuously, many African steelmaking traditions were lost to colonial disruptions and economic shifts. Today, experimental archaeologists work with Tanzanian elders to reconstruct these ancient methods, reverse engineering techniques that once made the region a metallurgical powerhouse. As modern blacksmiths recreate the process using traditional materials, the steel that emerges rivals modern alloys, a powerful reminder that innovation isn't always about moving forward. Sometimes it's about remembering what we've forgotten. Deep in the Taoist alchemy labs of 9th century China, where scholars sought immortality in bubbling crucibles, an accidental discovery would ignite a revolution, not of eternal life but of unprecedented destruction. While mixing saltpeter, sulfur, and charcoal to create a life-prolonging elixir, Tang dynasty chemists instead unleashed a deafening blast and searing flash. Rather than discarding this volatile powder, military strategists saw its potential, dubbing it Huo Yao, fire medicine. What began as a failed potion became history's most transformative explosive, reshaping warfare from the Great Wall to the battlefields of Europe. The earliest gunpowder weapons weren't cannons but psychological terror tools. Song dynasty engineers designed flying fire arrows, bamboo tubes packed with gunpowder strapped to arrow shafts that screamed through the air, trailing flames. At the Siege of Dan in 1132, Song defenders unleashed primitive grenades called thunderclap bombs, iron casings filled with gunpowder and shrapnel that produced deafening booms and lethal fragmentation. Contemporary accounts describe Jurchen soldiers shaken to their souls by these early explosives, their horses stampeding in panic. The real game changer, though, was the fire lance, a bamboo tube shooting flames and pellets, essentially the world's first flamethrower. These weapons evolved rapidly. By 1280, Yuan dynasty troops wielded metal-barreled bombards capable of breaching city gates. Gunpowder's spread westward wasn't just a transfer of technology, it was a slow-motion quake that toppled medieval power structures. Islamic chemists in the 13th century refined Chinese formulas, increasing saltpeter ratios for greater blast strength. Mamluk warriors used these enhanced mixtures against crusaders at the Battle of Ain Jalut in 1260, where explosive Madfar cannons helped secure victory. When knowledge reached Europe via the Silk Road, it catalyzed an arms race. By 1453, Ottoman supercannons like the massive Basilica reduced Constantinople's mighty walls to rubble, marking the end of an era where castles guaranteed safety. Yet the most fascinating aspect of gunpowder's journey isn't its destructive power, but its paradoxical role in driving scientific progress. The same explosions that shattered armies also shattered old ways of thinking. Alchemy's mystical pursuits gave way to empirical chemistry as researchers sought purer saltpeter extraction methods. The physics of projectile motion, once explained by Aristotle's flawed theories, was rewritten by mathematicians tracking cannonball trajectories. Even the arts transformed fireworks. Displays in Renaissance Europe echoed Chinese pyrotechnic traditions, blending chemistry with spectacle. What lingers today isn't just the echo of ancient blasts, but the realization that progress often emerges from unexpected failures. Those Tang alchemists never found immortality, yet their failed experiment birthed a force that made kings tremble, reshaped continents, and ultimately propelled humanity into an age where firepower and knowledge became irrevocably intertwined. The legacy of Huo Yao whispers a timeless truth. Sometimes the most world-changing discoveries aren't the ones we seek, but the ones that explode unexpectedly into history. Long before the first pharmaceutical labs synthesized pain-relieving compounds, indigenous healers across the Americas were already harnessing nature's own medicine cabinet with remarkable precision. In the dense forests of the Northeast, Algonquin tribes brewed willow bark tea to ease fevers and joint pain, a remedy later revealed to contain salicin, the chemical ancestor of modern aspirin. Meanwhile, high in the Andes, Inca surgeons chewed coca leaves before procedures, their numbing saliva acting as a local anesthetic for trepanations and wound care. These weren't random folk traditions, they were the product of generations of careful observation, where healers tracked which plants soothed specific ailments with the methodical rigor of any clinical trial. The science behind these ancient analgesics is startlingly sophisticated. When willow bark is soaked in water, its salicin converts to salicylic acid, a compound that inhibits prostaglandins, the same pain-signaling molecules targeted by today's ibuprofen and naproxen. Pre-Columbian healers didn't know the biochemistry, but they recognized willow's anti-inflammatory properties through trial and error, often combining it with other plants to enhance effects or mitigate side effects. Similarly, coca leaves contain alkaloids like cocaine, not the processed drug, but the natural compound that block nerve endings from transmitting pain signals. Spanish chroniclers recorded Inca runners chewing coca during long-distance journeys to endure altitude sickness and fatigue, a practice later adopted by colonial miners working brutal shifts in Potosi's silver mines. Contrast this with modern pharmaceuticals and a fascinating duality emerges. While a Bayer chemist first isolated pure acetylsalicylic acid in 1897, creating standardized aspirin tablets, indigenous preparations offered built-in safeguards. Willow bark tea contains buffering tannins and flavonoids that protect the stomach lining side, effects that synthetic aspirin would later require additional medications to address. Pharmaceutical cocaine, isolated in 1859, became a dangerous recreational drug, while traditional coca use in South America rarely leads to addiction when consumed in whole leaf form with its natural alkaloid balance intact. The difference lies in what scientists now call the entourage effect, the notion that whole plant remedies work better than isolated compounds because hundreds of interacting components modulate each other's effects. Yet the story of these painkillers is also one of cultural erasure and rediscovery. When European colonists demonized indigenous healing as witchcraft, generations of medical knowledge nearly vanished. It took until the 20th century for researchers to systematically study these remedies, often relying on ethnographic records compiled by rare, open-minded missionaries. Today, the pendulum is swinging back. The World Health Organization estimates 75% of modern drugs derived from plants were first used in traditional medicine, from aspirin to the cancer-fighting vinca alkaloids of Madagascar's rosy periwinkle. Pharmaceutical companies now partner with tribal councils to ethically source and study ancestral remedies, a belated acknowledgement that the world's oldest pharmacies might still hold undiscovered cures. The legacy of these Native American painkillers challenges our assumptions about medical progress. In an age of synthetic drugs and high-tech solutions, their example reminds us that sometimes the most effective remedies grow quietly at our feet, waiting not for a lab, but for the wisdom to recognize their worth. As we grapple with opioid epidemics and antibiotic resistance, these ancient approaches whisper an alternative path, one where healing works with nature's complexity rather than attempting to reduce it to a single molecule. From the Antikythera Mechanism's celestial predictions to the Inca's surgical mastery of trepanation, these 30 discoveries shatter the myth of ancient societies as primitive. Each artifact, whether Baghdad's potential batteries, Rome's self-healing concrete, or the mathematical brilliance encoded in Babylonian clay, proves our ancestors weren't just stumbling toward progress, they were leaping ahead with insights we're only now beginning to decode. The Mayan astronomers tracking Venus with naked eye precision, The Tanzanian steelmakers forging alloys rivaling modern metallurgy, the Aboriginal songlines mapping supernova explosions, none of these feats fit the outdated narrative of linear advancement. Instead, they reveal a tapestry of parallel genius, where cultures separated by continents and centuries arrived at astonishingly sophisticated solutions to universal human challenges. These innovations force us to reconsider what advanced truly means. A Gupta Empire iron pillar stands rust-free after 16 centuries, while today's bridges crumble within decades. Chinese seismoscopes detected distant quakes without electronics, and Egyptian pregnancy tests harnessed biochemistry millennia before laboratories. Even technologies we consider modern, from nanotechnology in Damascus steel to passive cooling in Persian yakchuls, have roots reaching back further than most textbooks acknowledge. The common thread, a profound intimacy with natural materials and phenomena, cultivated through generations of observation rather than controlled experimentation. Yet for every discovery we've unearthed, countless others likely vanished without a trace. The Antikythera Mechanism hints at a lost tradition of Greek mechanical engineering. The Mayas' burned codices may have contained astronomical data surpassing even the Dresden Codex. What revolutionary concepts perished with the Library of Alexandria's flames, or the oral traditions of indigenous cultures severed by colonization? The haunting possibility remains that some ancient breakthroughs were so far ahead of their time, we lack even the context to recognize their fragments when we find them. This isn't just about marveling at the past, it's about humility. As we stand atop our digital towers, we might ask, which of today's groundbreaking technologies will future civilizations rediscover in ruins, realizing we'd merely reinvented what others perfected long before? Perhaps the real lesson lies not in chronological superiority, but in recognizing that human ingenuity flares brightly across all eras, often in ways that defy our assumptions. Now we turn to you. Which of these ancient innovations most reshaped your view of history? Was it the Viking sunstones guiding ships through fog, or the Roman hypocausts whispering secrets of sustainable heating? Share your thoughts below, and if you're hungry for more mysteries hidden in plain sight, subscribe to keep unraveling history's greatest puzzles with us. The past isn't just a prologue, it's a mirror reflecting possibilities we're only beginning to imagine.